Okay, in this video we're going to look at orthogonal function series. So this is based on the theorem which says if we have a set of functions phi n and this set is orthogonal in an interval ab with respect to the weight function w, then any piecewise continuous function in that same interval can be represented by a uniformly convergent series expansion given by this equation number 1 here. The coefficients in this equation are given by this formula, let's call it number 2. Okay, in an earlier video entitled orthogonal functions, we have explained the concept of orthogonal function. You might want to check it before you continue this video if you're not up to speed with that concept. All right, so what we're going to do here is we're going to derive this equation number 2 from equation number 1. And the way this works is we multiply 1 by w times phi m, and then we integrate over the interval ab. Integrate over ab. So when we do that, so let's just multiply first. So we're going to multiply through here by phi m times w. So on the left hand side we're going to have w f times phi m. First term is going to be a naught phi naught phi m. Second term is going to be a1 phi 1 phi m, and so on and so forth. Using the summation notation, since phi m does not depend on n, our dummy variable here, dummy summation variable, we can multiply into the summation. So it's going to be an phi n times phi m. Okay, so that's just multiplying by w phi m. And then after that we integrate from a to b. So when we integrate, this is what is going to happen. So on the left hand side we are going to have w f times phi m dx. Now on the right hand side we're going to integrate each of these accordingly. I'm just going to go and do it in the shorter summation version. So this is going to be an into the integral from a to b of sorry, there is supposed to be w there, so w phi m times phi n dx. Now from the orthogonality properties, when we integrate each of these should have w. When we integrate each of these, they are going to be, the integrals are going to be 0 so long as the two indices here are different, the only one that is going to be non-zero is the one where these two are the same. So that means integrating into this summation is going to break the summation into just a single term, because all the terms when these two are different are going to vanish. So the only one that's going to survive is the one where m is equal to n. So for that case, we're going to write am integral from a to b w times phi m squared dx. So that's going to be the only term that survives in this summation. And then from here we can make am the subject of the formula. So am is going to be equal to the term on the left hand side, so integral of wf times phi m dx divided by the integral of w phi m squared dx, and this completes the derivation of formula number 2. Okay, so what we're going to do now is we're going to look at the particular case of Legendre polynomials, which we have seen that they are orthogonal. Okay, so we're going to look at the particular case of Legendre polynomials. So for these polynomials, we're going to be interested in this denominator term of the formula for the coefficient. So for these polynomials, we know that the interval of orthogonality is -1 to 1. The weight function is 1, and the integral of Pn squared dx is 2 over 2n plus 1. So if we take this and plug it in here, it means if we have a Legendre polynomial series, P0, A1, P1, A2, P2, then An is going to be given by, so it's going to be the reciprocal of this, so 2n plus 1 all over 2, and then this is going to be into the integral from -1 to 1 of f of x times Pn of x dx. So that's going to be our formula for finding the coefficients. So let's look at a few examples. All right, so we're going to look at these examples. In these examples, we're going to find the first 3 non-zero terms of the Legendre polynomial series of these functions. So let's call this our formula number 3. So that's the formula we're going to use to find our Legendre series coefficients. I've just put the first 4 or 5 Legendre polynomials here for reference. So in the first question we have got 4x minus 1. So we're interested in this function in this interval. Okay, so according to that formula number 3 here, so for a0, so that's just going to be 1/2, that's going to be p0, which is 1. So that means a naught is going to be 1/2. So this is just going to be the integral of the given function. Now, since 4x is an odd function, that means the contribution from this term is going to be 0 straight away. So we're only interested in this term really, so its integral is going to be 1/2 negative x minus 1 to 1. So it's going to be negative 1/2 1 minus negative 1. So this is going to be negative 1. So that's a naught. And then a2, we're going to have 3/2. Then it's going to be the function times p1. P1 is x, so it's just going to be the function times x. So we're going to have 4x squared minus x. So this time the term that is odd is this one. So the only term that's going to make a contribution for our calculation is that 4x squared. And so if we integrate that, it's going to be 3/2. So it's going to be 4/3 x cubed minus 1 to 1. So that's going to be 2 into 1 cubed minus negative 1 cubed. So this is going to be 4. So that's a1. Then a2 is going to be 5/2. Then we are going to have integral from minus 1 to 1. This is f of x, and this is p2. Okay. If we multiply out here, so that's going to be 5/4. Multiply out here, this times this is going to give us 12x cubed. And then 3x squared times negative 1 is minus 3x squared. And then minus 4x if multiply these two. And then plus 1 dx. Then again, this is symmetric integral. So all the odd terms are going to contribute 0. These are the two odd terms. So this is simply 5/4 integral of minus 3x squared plus 1. So let's integrate this. 5/4. So this is going to be negative x cubed plus x. Actually, what I'm going to do here, because these terms are even, so what we're going to do here is integrate from 0 to 1 and multiply by 2. So that's what we're going to do. So this is going to be 5/2. So now 0 to 1, just the contribution from 1 is important, and you can see that that is going to be 0. In fact, we can prove that. So the question is looking for the first 3 non-zero terms. So this third one is 0. We can prove, we're going to leave it as an exercise. It can be shown that an 2n plus 1/2 of the form for x minus 1 times Pn, dx is 0. This is going to be 0 for all n values 2 or greater. Okay, so I'm going to leave this as an exercise. All right, so the only two non-zero ones are the a0 and a1. a0 is -1. So what this means is that therefore f of x is a0 is -1. So -1 times p0. a1 is 4 times p1. And that's all. Now remember, p1 is x. So for p1 is x, p0 is 1. So this is just recovering exactly the same function that we started with. And this will typically be the case whenever you are representing a polynomial using Legendre polynomials. So the Legendre polynomial series is always just going to recover the polynomial that you started with. Okay, in part B we have got a function that is given by 0 on the left hand side of the origin and square root x on the right hand side of the origin. So this function is going to look something like this. So on the left hand side going to be 0, and then on the right hand side it's going to be the square root function. Okay, so yeah, there's a piecewise continuous function. So a0 is simply 1/2 times the integral of f of x. Now f of x this time is 0 from -1 to 0. So that means actually the only contribution is going to be on the right hand side. So that's what we're going to have. If we integrate this, we're going to have 1/2 times 2/3 x to the power 3/2. So this is going to give us a third. So that's going to be our a0. Then a1 again. So only the contribution on the right hand side of the origin is going to matter. So it's going to be p1 times f. So this time we're integrating x to the power 3/2. So it's going to be 2 on 5, x to the power 3/2, 0 to 1. So this is going to work out to 2/5. So that's the second one. And then the third one, well, if it's a non-zero, so this is going to be 5/2 integral from 0 to 1. So we're going to have square root x times p2 is 1/2 3 x squared minus 1. So this is going to be 5 on 4. The integral of that's going to be 5/2 minus x to the power 1/2. So yeah, we're going to integrate this. So 5 on 4 is going to be 3 times 2/7. X to the power 7/2 minus 2/3 x to the power 3/2 integrated from 0 to 1. Okay, if I plug in the limits, this is going to work out to 5/25. So that means our Legendre polynomial, the first three terms of our Legendre polynomial series of this function, is going to be p0 over 3 plus 3p1 over 5 plus 5p2 over 21. All right, what we are going to do now is we are going to give you an opportunity to have a go at this part C. Just pause the video and work through it. And then when you press play, then you can compare with our solution. All right, let's now look at our solution for part C. So in part C, we've got absolute value function between -1 and 1. So we know that the absolute value is given by x, well, if it's absolute value of x, for x greater than 0, it's given by negative x when x is less than 0. Graphically, it looks like this. And from this, you can see that it is an even function. All right, so let's work through the coefficients. So a0 is going to be 1/2 into the integral of mod x dx. Since this is even, we can just integrate from 0 to 1, use x, and multiply this integral by 2. So this half is going to work out to 1. And then integrating, that gives us 1/2. Then for a1, on the left hand side, this becomes negative x. Remember, p1 is x, so this is going to work out to negative x squared. And then on the right hand side is going to work out to x squared. We integrate, it's going to give us negative 3/2 times x cubed over 3. This time it's the same thing but positive. Those are the limits, and then when we plug this in, finally it gives us 0. Well, we could have just seen this by or from the fact that we have here so x p1 is x, which is an odd function, and our function is mod x, which is an even function. Now whenever you multiply an odd function by an even function, then the resulting function is going to be an odd function. So that's why, for instance, so x squared is even if you multiply it by an odd function, say x, and then this gives us x cubed, which is odd. So this function here is odd, and on account of that, because we've got a symmetric integral, that's going to be 0 straight away. All right, then we go to a2. So in this case, this is even, this is even function times even function gives another even function. So we can simply integrate this from 0 to 1 multiplied by 2, and in which case mod x is just going to be x. So integrating there and substituting accordingly gives us 5/8. a3 is also going to be 0 by the same argument that we put there. In fact, these things are such that if the function of interest is even, then when you represent it in terms of Legendre polynomials, only the even polynomials will contribute. If the function on the other hand is odd, then you can't use even polynomials to create an odd. Any linear combination of even polynomials is going to be another even function. So on that account, a3 is going to be 0. So because we're looking for the first 3 non-zero terms, we have got to go to a4. So there we go, same process. So that's even, so we can integrate from 0 to 1. This becomes x, and then we integrate and plug in. So this time we're going to get minus 3 over 16. And so the first non-zero terms are going to be these ones here for the absolute value function. All right, thank you for watching. Please do subscribe to support the channel, and put comments at the bottom for particular topics you want us to cover, etc., and like the video. Thank you.